We're going to go over problem number 16 on your review. And if you guys are having problems, the best thing for you to do is to pause and stop this video and try to do it before I do it. Or at the very least, when I'm all done, then see if you can do it yourself. But if you're just watching this and writing things down, that's not a good idea to judge if you really understand what's going on. So let's read this problem. We have 150 milliliters of 0.25 molar potassium hydroxide. So these guys all go together. And it's combined with 150 milliliters of 0.01 molar copper. Okay, so let's just underline that guy. And so what I have here is I have two things that I'm combining. So I have a reaction. I have numbers for both reactants, which means I need to see if I have a limiting reactant problem. And to do that, the first thing you have to do is write this balanced equation. And remember, copper 2 means this is a +2 and that's a -2. Crisscross your charges. You'll see over here, this is a +2. Hydroxide's a -1. So when I crisscross, I get a 2 there. But of course, these guys don't really have charges. That's just a shortcut. So this is my balanced equation. The other thing to know is we're finding percent yield, and we have a precipitate that's isolated. So you are going to have to use your solubility rules, and you will find that this is your precipitate. So this is what was actually done in the lab, and now I have to find out what theoretically should have been produced. And so what we have is we can find moles by doing molarity times liters, okay? And that works for copper hydroxide, which is 0.0375, and I'm just going to put that in my BCA chart right there. And then I do copper sulfate, same thing. Remember, molarity times liters equals moles. Okay, so that's what I did, and I got this. And now what I notice is I have a 2-to-1 ratio. So I have to figure out which one runs out. Now for me, let's erase this. I usually look at this. I have one of these and I need 2 of these. That means I need double. So if I have 0.0015 and I double it, that's gonna be 0.003. I have way more. So this is gonna be my excess and this is gonna be my limiting reactant. And remember, this is just a mole ratio. I have 0.0015 copper sulfate. I don't want copper sulfate, I want copper hydroxide. And so that is a 2-to-1 ratio. That's going to be double, which is going to give me 0.0030. So I have plenty. So I am going to use, if I have that, which I use up, so minus 0.0015, that leaves me nothing there, and minus 0.0030, which is going to leave me 5,430. Okay, so a lot of copper hydroxide left. But right now, in order to find my yield, this is my precipitate. That tells me I have to find this guy, which is my solid precipitate. And this is a 1-to-1 mole ratio. So if I use this much, how much of this will I make? Well, it's a 1-to-1 mole ratio. So if I put 1-to-1 there, I'm going to get the same number, 0.0015. And it doesn't ask me anything about this. It's going to ask me about pH later. So that's talking about OHs, and we'll talk about that in a second. So 0.0015. And just in case you forget, before a reaction, that's 0. This is a 1-to-1 ratio also. 2 sulfates, yep, that's balanced. Okay, so this is how many moles. Remember, my BCA chart is moles. but they gave me my actual yield as 11 grams, and it said for my precipitate, so my precipitate is copper hydroxide. Why? Because that's my solid. Okay, so I need to change this moles into grams. Here is my molar mass of copper, so 0.0015 moles, of copper hydroxide. And, let's move this over a little. I'm not on that. Okay. So I'm getting rid of my copper hydroxide moles, and I'm going to grams of copper hydroxide. And my molar mass was 97.56. So I need to multiply those together. Okay, I cleaned that up a bit. So I take my moles right here of my copper hydroxide, and I calculate that to be 0.015 grams of copper hydroxide. Now, since I figured this out, it didn't really happen in a lab. That's my theoretical. This is what I should have produced, but I only produced 11 grams. So actual over theoretical, you get 73% yield. What is the excess reactant? The excess reactant right here is copper hydroxide. Okay, what is the concentration of the leftover excess reactant? Now, what they're trying to get to is they're trying to find the pH of this solution. So let me just remind you of what's in solution when it's all said and done. I have solid copper hydroxide, that's on the bottom, CuOH2. That's solid. And so that's not ions in solution. So that does not affect my pH at all. Okay. And then I have some K plus and K plus and some SO4 2 minus. That's also in there. But then I have excess K plus. There's my excess there. And I also have some OH minus. And it is this for my excess reactant that is in solution. So this OH is what's going to be my pH. So if I can find the concentration, I can convert it to pH. So this gets a little tricky. My molarity is moles divided by liters. Now, I need to figure out what the moles are there, which we'll do in just a second. But then I also need to find out the liters of solution. So what went in here? 150 milliliters of KOH plus 150 milliliters of copper sulfate, which gives me 300 milliliters of solution. Okay, I have that right there, or 0.3 liters. So we have our liters, and then we have our moles of potassium hydroxide, which is 0.0345 moles. And when I put that in my calculator, I get 0.0345 divided by 0.3 equals 0.115 molarity. Okay? So this is my molarity of my KOH. And what happens is it turns out it's also the molarity of my OH, because KOH goes into the solution, it makes 1 K and 1 OH. So if I have when I break this down, I have one of these breaks up into one of these and one of these, and they're in the same amount of solution. So my molarity, my concentration is going to be the same for each of these species. It's a 1 to 1 to 1 ratio. This is my OH concentration. So if I have my 0.115 molar OH, I can turn that into H3O, which we all know is H plus as well, same. And I'm going to plug it in 1 times 10 to the negative 14th equals concentration of my OH times my H plus, and divide to get a lone. I get my concentration of my H plus or my H3O plus is 8.7 times 10 to the negative 14th. If I take the log of that, I can find my pH, which is 13.1. This tells me this is a basic solution. And if we look back here, that makes sense because I have a base that's reacting, and this is my excess. My excess was a base, so I should have a basic solution. So that's how you solve that guy.